Today's lecture is about the death of stars. How do stars die? To understand the answer to that question, we must first remind ourselves what a star is. Take the Sun, our star. The Sun is a big ball of glowing gas, 1.5 million kilometers in diameter, 6,000 degrees hot. The amount of energy emitted by the Sun is a staggering 4 times 10 to the 26 watts. That's a 4 with 26 zeros. We are fortunate to be 150 million kilometers away, so that we receive 1400 watts per square meter. And that's why life is possible on Earth. How does the Sun produce all that energy? Well, the Sun is very, very heavy, so the gas in the center is enormously compressed by the weight of the gas layers on top of it. That compression heats the gas. Inside the Sun it's 16 million degrees. And that makes nuclear fusion possible. Hydrogen is turning into helium at the rate of 600 million tons per second. 4 million tons per second of the matter disappears. It is converted into heat through E is mc squared. What this tells you right away is that there must be an end to the life of the Sun. The hydrogen fuel is being used up, so at some point it must run out. That's when the Sun will start to die. We know how much hydrogen there is, so we know when it will run out. In 5.5 billion years from now. The Sun is about 4.5 billion years old right now, so we're about halfway. When the hydrogen runs out, briefly the Sun becomes a red giant star. It swallows the Earth, but then it dies. What happens is that basically gravity, which has been trying to collapse the Sun all along, takes over and wins. Gravity in the end always wins. A star is basically a sponge gravity squeezes the energy out of, and when the energy is gone, gravity takes over. So the Sun collapses, it becomes a few thousand kilometers in size, about as big as the Earth, but it still has the mass of a star, so the matter has been compressed enormously. It's about 1 million times as dense now. Such a collapsed star is called a white dwarf, because initially it's white hot and it takes a very long time to cool down. So why doesn't the Sun collapse completely under its own gravity? Well, the electrons inside the white dwarf cannot come closer together due to quantum mechanical repulsion between them. That makes white dwarf matter very hard. It is basically the same principle that keeps atoms from collapsing. The ordinary atoms that make up this table, for example, are also hard. So, a star like the Sun lives 10 billion years. The universe is 13.7 billion years old, so lots of stars born long ago have already died. And they've turned into white dwarfs. We have something like 10 billion white dwarfs in the galaxy. The nearest one is in orbit around Sirius. Okay, so what about other stars than the Sun? How long a star lives depends on two things. How much nuclear fuel it has and how quickly it burns that fuel. These both depend on how heavy the star is, how massive it is. Really massive stars, more than 10 times the Sun, have a very different life from the Sun and they die very differently too. Take for example a star 20 times the mass of the Sun. Such a star basically has 20 times the fuel, but we can see that it is 40,000 times brighter. So it burns the fuel 40,000 times as fast. Hence, it dies after just 5 million years instead of billions of years. It lives 2,000 times faster than the Sun. Such stars do not turn into white dwarfs when they run out of fuel and collapse. The quantum repulsion of the electrons is too weak and gravity pushes the electrons into the protons to form neutrons. Now neutrons are very hard. They push each other away with the strongest force in nature, appropriately called the strong force. So a neutron star can form. 1.5 to 2 times the mass of the Sun, but only 20 kilometers in diameter. It has enormous density. 1 teaspoon of neutron star matter weighs 5.5 billion tons, about 1,000 big pyramids of Giza. It would also explode like a trillion megaton nuclear bomb, by the way. For even heavier stars, more than 25 times the Sun or so, not even the strong force between the neutrons nor their quantum repulsion is strong enough to counter gravity. No known physics can prevent their total collapse. When these stars run out of nuclear fuel, gravity wins completely. What happens is that all mass is compressed into a single point, the singularity. Basically it disappears from our universe, leaving only its fossil gravitational field. From within a sphere of a few tens of kilometers, nothing can escape, not even light. The gravitational field has, quite literally, produced a hole in the fabric of curved space-time. This is, of course, a black hole. While the core of the massive star collapses to form a neutron star or a black hole, its outer layers are thrown off in an enormous explosion, a supernova. For a few weeks or so, the explosion outshines its entire galaxy of hundreds of billions of stars. We can observe these explosions, they happen roughly once per century per galaxy, and we can see them across the universe. They tell us that a massive star died, but a neutron star or a black hole was born. This has been going on since the beginning, so there are maybe 1 billion neutron stars in our galaxy right now and 100 million black holes. In the explosion, the outer layers of the star are blown off into space, and they remain visible for hundreds of years as a cloud of glowing gas expanding at thousands of kilometers per second. For example, the Crab Nebula, the remnant of a supernova explosion observed by the Chinese in the year 1054. So that's the story of the end of the life of a star. Fuel runs out, the star collapses. Because the universe is still so young, it is interesting to wonder what will happen far into the future. What we saw was that everything depends on the mass of the star. If you take a star 10 times as small as the Sun, it has 10 times less hydrogen, but these are really tiny, dim red stars. They burn their fuel extremely slowly, so they live much longer than the Sun, 1,000 billion years or so. So in our universe of 13.7 billion years old, none of these stars have died yet. That's something for the deep, deep future. There are lots of these stars, and we predict that in the end they're all going to end up as white dwarfs. Of course, new stars are still born every day, but those stars will eventually die as well. So, in the end, a few 100,000 billion years, all stars will have died and cooled down, and no new ones are forming anymore. That will be the end of the stellar era of the universe. Is that the end of history?